close your eyes for a moment and imagine standing beneath a night sky so crowded with stars that darkness itself seems like a forgotten concept. Every direction you look, light pours down from billions of distant suns, each one burning hydrogen into helium, each one pouring energy into the vast cosmic ocean. The Milky Way stretches overhead like a river of light, and in the spaces between the stars, faint glows mark distant galaxies, each containing hundreds of billions of stars of their own. This is the universe as we know it, a place of light and energy, of nuclear furnaces scattered across unimaginable distances, of constant motion and transformation. It feels eternal. It feels as though it will always be this way. Stars have been shining for billions of years before human eyes ever opened to see them, and they will continue shining for billions more. The night sky feels permanent, a fixed backdrop against which our brief human stories unfold. But permanence is an illusion, a gentle lie we tell ourselves because our lifetimes are so short that we cannot see the slow turning of cosmic wheels. The truth, when you let it settle softly into your thoughts, is both beautiful and melancholic. The universe of stars, this brilliant age of light and fusion, is temporary. It is a phase, a chapter in a much longer story. And like all chapters, it will end. Not tomorrow, not in 1,000,000 years, not even in 1,000,000,000. The timescales we are about to explore are so vast that human language struggles to capture them. But end it will. The stars will go out, one by one, until the last nuclear fire flickers and fades. And after that, the universe will enter a different age entirely. A long, slow, cooling age that will last far longer than the age of stars ever did. Tonight, we are going to take a journey together, a gentle journey into deep time. Tonight, we are going to take a journey together, a gentle journey into deep time. We will watch as the universe slowly transforms from the bright, energetic place we know into something quieter, darker, and colder. We will witness the formation of the last stars. We will see them burn through their fuel and fade into remnants. We will explore the long ages that follow, when black holes rule the cosmos, when even atoms themselves may dissolve, and when the universe becomes so empty and still that time itself loses much of its meaning. This is not a journey of fear or dread. There is no catastrophe coming, no sudden apocalypse. What we are exploring is simply the natural unfolding of physical law across timescales that dwarf human comprehension. It is a story of endings, yes, but also of patience, of the universe following its own rhythm, unhurried and inevitable. Let your breathing slow. Let your thoughts soften. As we move through this story, allow the immense scales of time and space to wash over you like gentle waves. Do not try to hold every detail. Instead, let the images flow through your mind. Let the words become a steady current, carrying you deeper into calm. The universe's far future is not a place of urgency. It is a place of profound stillness, of change measured not in years or centuries, but in trillions upon trillions of years. We live in what cosmologists call the stelliferous era, the age of stars. It began roughly 200 million years after the Big Bang, when the first generation of stars ignited in the primordial darkness. Before that, the universe was filled with hydrogen and helium gas, glowing with the fading heat of creation, but containing no stars, no galaxies, no structure as we recognize it. Then gravity began its patient work, gathering gas into denser and denser clouds until the cores of these clouds grew hot enough for fusion to begin. Then gravity began its patient work, gathering gas into denser and denser clouds until the cores of these clouds grew hot enough for fusion to begin. And there was light. The first stars were giants, massive beyond anything we see in our local neighborhood today. They burned fierce and fast, living only a few million years before exploding as supernovae, scattering heavier elements into space. Those elements, forged in stellar cores and supernova fires, became the raw material for the next generation of stars. And so the cycle continued, with each generation building on the ashes of the last, creating more complex chemistry, more variety, more structure. Our sun is a relative latecomer to this story. It formed roughly 4.5 billion years ago, about 9 billion years after the Big Bang. By that time, the universe had already lived through countless generations of stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged inside stars that lived and died before our solar system even existed. You are made of stardust, not as poetry, but as plain physical fact. But here is what matters for our journey. Star formation. This process of turning gas into shining nuclear furnaces has been slowing down for billions of years. The peak of star formation in the universe occurred roughly 10 billion years ago. Since then, the rate at which new stars form has been declining steadily. The universe is not creating stars as quickly as it once did, and this trend will continue. Why? Because star formation requires fuel, specifically hydrogen gas, and the universe has a finite supply. Some of that hydrogen has already been locked up inside stars. Some has been blown out of galaxies by supernova explosions and powerful stellar winds. Some exists in forms or locations where it cannot easily collapse into new stars. Some exists in forms or locations where it cannot easily collapse into new stars. The great gas reservoirs that fed star formation in the early universe are being depleted, and they are not being replenished fast enough to maintain the old pace. This does not mean the stars will all blink out suddenly. Far from it. Stars live for different lengths of time depending on their mass. The most massive stars, the brilliant blue giants that outshine our sun by factors of thousands or millions, burn through their fuel in just a few million years. Medium stars like our sun have lifetimes of roughly 10 billion years. But the smallest stars, the faint red dwarfs that make up the majority of all stars in the universe, can burn for trillions of years. Trillions. Let that word rest in your mind for a moment. A trillion years is a length of time almost impossible to grasp. The universe itself is currently only about 14 billion years old. 14 billion. A trillion is 1,000 billion. The universe would need to live more than 70 times its current age before a trillion years passed. And the smallest red dwarf stars can burn for not just 1 trillion years, but many trillions. Perhaps 10 trillion, perhaps 20. They sip their fuel so slowly, fusing hydrogen so gently, that they stretch their supplies across unimaginable ages. These red dwarfs will be the last stars. Long after stars like our sun have swelled into red giants and faded into white dwarfs. Long after all the massive stars have exploded and collapsed into neutron stars or black holes, the red dwarfs will still be burning. Faint, cool, dim, barely visible even from nearby, but burning nonetheless. They will be the last lights in a darkening universe. The formation of the last star will not be a dramatic event. There will be no audience to witness it, no ceremony, no marker in space to commemorate the moment. Somewhere, in some galaxy, in a small cloud of hydrogen gas, gravity will gather matter together one final time. The cloud will contract, heat, and ignite. A faint red glow will appear, a star so small and dim that even from a few light years away it would be hard to see. And with that ignition, the age of star formation will quietly come to an end. Current estimates suggest this will happen roughly 100 trillion years from now. 100 trillion. Write it out, and it looks like this: 100 million years. Or in scientific notation, 10 to the 14th years. It is a number so large that all of human history, from the first stone tools to the present day, represents less than a millionth of that span. After that final star forms, no more will follow. The hydrogen gas needed to make new stars will be gone, locked up in existing stars, dispersed too thinly to collapse, or blown clear out of galaxies entirely. Star formation, the process that has lit up the universe for nearly all of its history, will cease. And the universe will enter a new phase, one defined not by birth and brilliance, but by aging and dimming. But we are getting ahead of ourselves. We have not yet reached that point. Right now, in this present moment, stars are still forming. Thousands of them ignite every day across the observable universe. In the Milky Way alone, roughly one new star forms each year on average. The universe is still bright, still active, still in the prime of its stellar age. Yet the decline has already begun. It is subtle, measured on timescales so long that no human lifetime could detect it, but it is real. The universe is slowly darkening. The peak brightness is already behind us. We are living in the long afternoon of the cosmos, when the sun is still high but beginning, almost imperceptibly, to descend toward the horizon. We are living in the long afternoon of the cosmos, when the sun is still high but beginning, almost imperceptibly, to descend toward the horizon. There is something both sad and strangely comforting about this realization. Sad because it means the universe of stars, this magnificent age of light, is not forever. Comforting because it places our moment in perspective. We are not living in some random, insignificant time. We are living in the age when the universe is most rich with stars, when galaxies are still bright, when the night sky is still crowded with light. Future observers, if any exist trillions of years from now, will inherit a much darker cosmos. They will never know the brilliant stellar age that we can witness every clear night. So as you settle into this journey, hold that thought gently. You are here, now, in the time when stars shine brightest. And over the next hours, as we explore what comes after, as we watch the last lights go out and follow the universe into its long, cooling future, remember that all of it is still ahead. For now, the stars burn. For now, the universe glows. For now, there is light. Let that light fill your mind as your eyes grow heavy. Let the image of a star-filled sky become a soft, warm backdrop to your thoughts. And as we move forward, as we step gently into deep time, allow yourself to drift along with the story. There is no rush. The universe has all the time in the world. More than all the time in the world. It has trillions of years to spend. And we are going to spend them together, slowly, calmly, watching the gentle unwinding of cosmic time. The last star has not yet formed, but it will. And when it does, it will mark the beginning of the end of an age. Not an end of the universe itself, but an end of the universe as we know it. The transformation will be slow, peaceful, inevitable. The transformation will be slow, peaceful, inevitable. And it starts, in a way, right now, as the fuel for future stars grows ever scarcer and the long dusk of the cosmos begins. Rest in that thought. Rest in the knowledge that change is slow, that endings take time, and that the universe moves at its own patient pace. As you breathe slowly in and out, imagine yourself floating in space, far from any star, watching the distant lights scattered across the darkness. Each one is a nuclear furnace, burning its fuel, shining its light into the void. And one by one, over timescales longer than imagination can hold, they will fade. But not tonight. Tonight, they still shine. And so do you. To understand what it means for the stars to fade, we must first understand what makes them shine. So let us take a moment, here in the gentle darkness behind your eyelids, to explore the life of a star. Not with equations or technical jargon, but with simple images and patient explanation. Let the concepts wash over you like soft waves, each one building on the last, creating a calm understanding of these magnificent objects that light up our universe. A star is not a bonfire in space, though it may seem that way from a distance. It is not burning in the chemical sense, the way wood burns in oxygen. A star is something far more profound. It is a sphere of gas, mostly hydrogen, held together by its own gravity. And at its core, where the weight of all that overlying material creates crushing pressure and searing heat, something extraordinary happens. Hydrogen atoms, normally separate and distant, are forced so close together that they overcome the electromagnetic repulsion that usually keeps atomic nuclei apart. They fuse. They merge. For hydrogen nuclei combine through a series of steps to form one helium nucleus. And in that transformation, a tiny amount of mass disappears. Not much. And in that transformation, a tiny amount of mass disappears. Not much. Less than 1% of the original hydrogen mass. But that vanished mass does not simply cease to exist. It is converted into energy, according to Einstein's famous equation. The energy released by fusing just 1 kilogram of hydrogen into helium is roughly equivalent to burning millions of kilograms of coal. And a star like our Sun fuses hundreds of millions of tons of hydrogen every single second. That energy, released in the core, works its way slowly outward through the star, taking thousands or even millions of years to reach the surface. It pushes outward, creating pressure that balances the inward crush of gravity. This balance, this perfect equilibrium between gravitational collapse and fusion pressure, is what keeps a star stable. It is what allows a star to shine steadily for billions of years without growing or shrinking, without exploding or collapsing. The star is in a constant state of controlled falling, held in perfect suspension by the energy generated at its heart. Not all stars are the same. They come in a remarkable variety of sizes, temperatures, and lifetimes. The most massive stars can be 100 times heavier than our Sun. They burn blue-white, searingly hot, with surface temperatures exceeding 30,000 degrees. They pour out light with such intensity that a single massive star can outshine millions of sun-like stars combined. But this brilliance comes at a cost. Massive stars burn through their hydrogen fuel at a prodigious rate. They may live only a few million years before exhausting their core fuel and meeting a violent end. Our Sun sits comfortably in the middle range. It is what astronomers call a G-type main sequence star, yellow in color, with a surface temperature of about 5,500 degrees Celsius. It has been burning steadily for about 4.5 billion years. And it will continue burning for roughly another 5 billion before it begins to change. It has been burning steadily for about 4.5 billion years, and it will continue burning for roughly another 5 billion before it begins to change. When it does, it will swell into a red giant, its outer layers expanding to perhaps the orbit of Earth, its core contracting and heating until it can fuse helium into carbon and oxygen. Eventually, it will shed those outer layers into space, creating a glowing planetary nebula and leave behind a hot, dense core called a white dwarf. But the stars that matter most for our story, the stars that will define the final chapter of the stellar age, are the smallest ones, red dwarfs. These are stars with less than half the mass of our Sun, often much less. Some red dwarfs have only about 8% of the Sun's mass, just barely heavy enough to ignite fusion in their cores. They are cool, with surface temperatures of only 3,000 degrees or so, and they glow a dull red or orange. From Earth, even the nearest red dwarf stars are invisible to the naked eye. They are simply too faint. Yet red dwarfs are by far the most common type of star in the universe. Roughly 3 out of every 4 stars are red dwarfs. They vastly outnumber all other types combined, and they have one extraordinary property that sets them apart from all others: longevity. A red dwarf can burn for trillions of years. Perhaps 10 trillion. Perhaps 20. Perhaps even longer. The universe is not old enough yet for any red dwarf to have run out of fuel. Every red dwarf that has ever formed is still burning today. This is because red dwarfs are incredibly efficient. They burn their hydrogen fuel so slowly, so carefully, that they stretch it across unimaginable spans of time. And unlike larger stars, red dwarfs are fully convective, meaning their interiors are constantly churning and mixing, bringing fresh hydrogen down to the core and carrying helium up and away. And unlike larger stars, red dwarfs are fully convective, meaning their interiors are constantly churning and mixing, bringing fresh hydrogen down to the core and carrying helium up and away. This allows them to access and burn nearly all of their hydrogen, not just the hydrogen in the core. While a star like our Sun can only fuse about 10% of its total hydrogen supply, a red dwarf can potentially burn through 70 or 80%. This is why red dwarfs will be the last stars. When all the massive stars have exploded, when all the sun-like stars have puffed up and faded, the red dwarfs will still be shining. They will outlast everything else. They will be the lighthouses of a darkening cosmos, faint but persistent, burning on and on as the universe around them changes beyond recognition. Right now, in this present moment 14 billion years after the Big Bang, the universe is in what might be called its golden age of stars. Not the brightest age, that was a few billion years ago, but still a rich and vibrant time. Star formation continues in countless galaxies. Massive stars explode as supernovae, enriching the interstellar medium with heavy elements. Sun-like stars nurture planetary systems. Red dwarfs glow quietly, barely noticed, yet outnumbering all others. The universe hums with stellar activity, with light and energy flowing from billions upon billions of fusion reactors scattered across space. But the fuel is running out. Slowly, imperceptibly on human timescales, but steadily nonetheless. Every star that forms locks away some hydrogen. Every supernova blasts gas out of galaxies. Every stellar wind pushes material into regions where it cannot easily collapse again. The great reservoirs of cold hydrogen gas that once filled galaxies are being depleted. In the Milky Way, star formation has already slowed considerably compared to the peak era 10 billion years ago. In the Milky Way, star formation has already slowed considerably compared to the peak era 10 billion years ago. The rate at which new stars form has dropped by a factor of 10 or more. The universe as a whole shows a similar trend. Astronomers looking at distant galaxies, seeing them as they were billions of years ago, observe more active star formation than we see in nearby galaxies today. The universe has been winding down its stellar production for a long time already. Current models suggest that star formation will continue for a long while yet. Not billions of years, but trillions. Small amounts of gas will continue to cool and collapse. Occasional collisions between galaxies will trigger new bursts of star formation as gas clouds slam together and compress. Existing gas will slowly settle into configurations where it can fragment and ignite. But the overall trend is clear and irreversible. The rate will continue to decline. Fewer and fewer stars will form as time goes on. Around 1 trillion years from now, give or take, star formation in the Milky Way will have essentially ceased. The last pockets of hydrogen gas will have been consumed or dispersed. The galaxy will contain all the stars it will ever have. And from that point on, it will be a story of subtraction. Stars will continue to die, but no new stars will replace them. The most massive stars will be long gone by then. Every star heavier than about 1 solar mass has a lifetime shorter than 1 trillion years, most much shorter. By the time the last star forms, the universe will have no blue giants, no sun like yellow stars, no orange stars. It will be a universe populated entirely by red dwarfs, plus the remnants left behind by all the stars that have already died. White dwarfs, neutron stars, black holes, the dead outnumbering the living. And then begins the long wait. The red dwarfs will burn on. 10 trillion years, 20 trillion, 50 trillion, 10 trillion years, 20 trillion, 50 trillion. The exact lifetimes depend on their masses and the details of their internal physics, and these calculations carry uncertainties. But the broad picture is clear. For an immense span of time, measured in tens of trillions of years, the universe will be lit only by these faint red embers. Galaxies will glow with a soft, ruddy light, far dimmer than they are today, but not yet dark. Imagine, if you can, floating in space in that distant future. You are somewhere in what was once the Milky Way, though by then it will have merged with Andromeda and several smaller galaxies to form a single large elliptical galaxy. The sky around you is mostly dark. The bright spiral arms, the dense star fields, the glowing nebulae, all of that is gone. What remains is a sparse scattering of faint red stars, separated by vast distances. Each one glows with a dull, ember-like light, barely visible unless you look directly at it. There are no bright blue stars to dazzle the eye, no sun-like stars to provide warm, familiar yellow light. Just red, dim red, fading into the darkness. It is a quiet scene, a melancholic scene, but there is also a strange beauty to it. These red dwarfs are survivors. They are the last natural lights in a universe that is slowly going dark. They burn with a patience that defies comprehension, holding back the darkness for trillions upon trillions of years. They are the universe's way of lingering, of not giving up its light all at once, of stretching the age of stars across the longest possible span. And during all this time, around some of these red dwarfs, there may be planets, worlds tidally locked to their faint parent stars, with one side in eternal dim light and the other in eternal darkness. The surface of such a world might be cold, barely above freezing even on the lit side, but beneath frozen crust there could be liquid water heated by geothermal energy. The surface of such a world might be cold, barely above freezing even on the lit side, but beneath frozen crust there could be liquid water heated by geothermal energy. And where there is liquid water, there is at least the possibility of life. It is one of the most intriguing questions about the deep future. Could life exist in the era of red dwarfs? Could civilizations arise around these faint stars, living out their existence in the long twilight of the universe? They would inherit a very different cosmos than ours. Looking out at the night sky, they would see almost nothing. A few faint red stars nearby, and beyond that, darkness. The cosmic microwave background, the afterglow of the Big Bang, would have cooled to almost nothing, redshifted into undetectability. Other galaxies would be invisible, carried far beyond any possible observation by the expansion of space. To inhabitants of that era, it might seem as though the universe consists only of their galaxy, or perhaps just their local cluster of stars, floating in an infinite void. They would have no way to know that the universe was once bright, no way to discover the rich history of stellar ages that came before. The evidence would be gone, stretched and dimmed beyond recovery. They would be living in a universe that has already forgotten most of its own story. But that is still far ahead. For now, let us simply hold the image of that dim red future in mind and recognize it for what it is. Not the end, but a long, slow transition. A bridge between the universe we know and something even quieter, even darker, that lies beyond. The stellar era we live in now is special. It will not come again. Once the last star forms, once the red dwarfs begin their impossibly long burn, the universe will never again see the brilliant blue giants, the warm yellow suns, the rich variety of stellar types that populate our current night sky. The age of diverse stars will be over. The age of diverse stars will be over. And the age of red dwarfs, the last age of natural light, will stretch across a span of time so long that the entire history of the universe up to now, all 14 billion years, represents barely a flicker at its beginning. Let that image settle into your thoughts as you breathe slowly, deeply. The stars will burn for so much longer than they already have. The universe is still young, still in the early chapters of its story. And yet, even in this youth, the end is already written into the laws of physics. The fuel is finite. The process is irreversible. The lights will go out. Not soon. Not in any time frame that has meaning for human lives or civilizations. But inevitably, this is not a cause for sadness. It is simply the way the universe is. Stars are not eternal, but they are patient. They take their time. They burn slowly. And in doing so, they give the universe long ages of light and warmth, long chances for complexity and structure, and perhaps even life to emerge and flourish. We are fortunate to live in the bright age, to see the Milky Way arching overhead, to study the life cycles of stars from birth to death, to know that we are made of star-forged elements, born from the ashes of earlier generations. This knowledge is a gift, one that may not be available to any future beings who arise in the dim, distant ages ahead. So as you drift toward sleep, hold an image of a star in your mind. Not any particular star, just the idea of one. A sphere of glowing gas, held in perfect balance, fusing hydrogen into helium, pouring light into the darkness. See it burning steadily, patiently, across billions of years. And know that billions more like it are doing the same, all across the universe, right now, in this moment. They are the heartbeat of the cosmos. And though that heartbeat will slow, will eventually fade, for now it continues. Strong and steady, lighting the universe, warming the darkness, burning on. Time moves differently when you measure it in trillions of years. Human minds are built for human timescales, days and months and years, perhaps a few generations at most. But as we move deeper into this story, as we follow the universe forward through spans of time that dwarf all of recorded history, it helps to let go of ordinary time sense entirely. Let the numbers wash over you without trying to grasp them. Let them become abstract, dreamlike, symbols of vastness rather than quantities you need to comprehend. The universe is patient. It does not rush, and neither should we. We have reached a point in our journey roughly 100 trillion years into the future. 100 million years. The last star has formed. Somewhere in some galaxy, in a final collapsing cloud of hydrogen, fusion ignited for the final time. A faint red dwarf, barely massive enough to sustain nuclear reactions, began its slow burn. And with that ignition, an age ended. The age of star formation, which began a few 100 million years after the Big Bang and continued for 100 trillion years, has come to a close. The universe at this point would be almost unrecognizable to us. The familiar structures we see today, the spiral galaxies with their bright arms, the irregular dwarf galaxies still actively forming stars, the brilliant quasars powered by supermassive black holes feeding on gas, all of that is gone. What remains are the products of 100 trillion years of stellar evolution and gravitational interaction. Most galaxies have merged. In the early universe, collisions between galaxies were common. Two spirals would encounter each other, their mutual gravity drawing them together over millions of years until they interpenetrated, their stars passing through each other like two clouds of gnats. Individual stars rarely collided. Space is too vast and stars too small, but the gravitational stirring would disrupt the orderly spiral structure, triggering bursts of new star formation and eventually merging the two galaxies into a single larger system. By 100 trillion years, this process has run nearly to completion. Most of the galaxies we see today have merged into larger elliptical galaxies, smooth and featureless. They're stars moving in random orbits rather than the organized rotation of a spiral disk. The Milky Way and Andromeda, along with the dozens of smaller galaxies in our local group, have long since merged into a single giant elliptical galaxy. Astronomers sometimes call this future galaxy Milkomeda, a blend of the two names, though of course no one will be around to call it anything. And these merged galaxies, these products of 100 trillion years of gravitational interactions, are now going dark. Not all at once, but gradually, as the stellar populations age and die. The massive stars went out long ago, within the first few billion years. The sun-like stars faded over tens of billions of years. Now only the red dwarfs remain, the faint ember stars that make up the vast majority of the stellar population. And they too have begun their slow decline. The longest-lived red dwarfs might burn for 50 trillion years, perhaps even longer. But even 50 trillion years is not forever. One by one, these faint stars are exhausting their hydrogen fuel. The fusion reactions in their cores are slowing, faltering, finally ceasing. As fusion stops, there is nothing left to hold the star up against its own gravity. The core contracts, growing hotter and denser, but it never reaches the temperatures needed to fuse helium. Red dwarfs are too small for that. They can only fuse hydrogen. When the hydrogen runs out, the fusion stops, and the star begins its long fade. What remains is called a white dwarf, though the white dwarfs left by red dwarfs are not quite the same as those left by sun-like stars. They are smaller, denser, composed mostly of helium rather than carbon and oxygen. But the principle is the same. A white dwarf is not truly a star anymore. It is a stellar remnant, the exposed core of a dead star, held up not by fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons in the core from being squeezed too close together. A newborn white dwarf is hot, searingly hot, with surface temperatures that can reach 100,000 degrees or more. It glows brilliant white or even blue-white, radiating away the residual heat from its previous life. But it has no internal power source, no fusion to generate new energy. It can only cool, and cool it does, slowly, over immense spans of time. A white dwarf cools at a rate that depends on its mass and composition, but the process is measured in billions of years. After the first billion years, a white dwarf that started at 100,000 degrees might have cooled to 10,000 degrees, glowing a warm white. After 10 billion years, perhaps 5,000 degrees, glowing yellow. After 100 billion years, a dull red, like a cooling coal. And the process continues. 100 trillion years. 1,000 trillion years. The white dwarf grows dimmer and dimmer, cooler and cooler. The red glow fades to deep crimson, to infrared, finally to wavelengths too long for human eyes to see even if there were human eyes around to see them. The surface temperature approaches the temperature of the surrounding space, and the white dwarf becomes essentially invisible. A dark, cold sphere of degenerate matter, floating in the darkness, no longer emitting any appreciable light. This is called a black dwarf, not to be confused with a black hole, which is something else entirely. A black dwarf is simply a white dwarf that has cooled to the point where it no longer glows. It is the final fate of every small to medium star. The universe is not old enough yet for any black dwarfs to exist. Every white dwarf that has ever formed is still cooling, still glowing, even if only faintly. But give it enough time, trillions upon trillions of years, and every white dwarf will eventually become a black dwarf. So imagine the universe at this stage, perhaps 200 trillion years after the Big Bang. The last red dwarfs have burned out. Star formation ended 100 trillion years ago. What fills the galaxies now is a population of stellar remnants. Billions upon billions of black dwarfs, dark and cold, invisible except by their gravitational influence. Scattered among them are neutron stars, the collapsed cores of stars that were too massive to become white dwarfs. These are also dark now. They formed hot, but like white dwarfs, they have no power source. They too have cooled over trillions of years, radiating away their heat, until they are barely warmer than the vacuum around them. And then there are the black holes. Stellar mass black holes, formed from the most massive stars, stars so heavy that even neutron degeneracy pressure could not hold them up. When these stars died, their cores collapsed completely, forming regions of space-time so warped that not even light can escape. These black holes do not cool in the ordinary sense. They do not radiate heat, but they are not entirely inert, as we will see later in our journey. The galaxy at this point is a graveyard, a vast collection of dark, cold remnants, most of them black dwarfs, drifting through space in complex orbits around the galactic center. There is almost no light, no fusion, no glowing gas, no bright nebulae, just darkness, broken only by the faint, rare events that still occur. Occasionally, two white dwarfs or black dwarfs will collide. The chance of any two stars colliding is incredibly small. Space is so vast and stars so tiny that even in a densely packed galaxy core, collisions are rare. But over trillions of years, rare events become inevitable. When two of these dense remnants do collide, the result can be a brief, spectacular flare. The kinetic energy of the collision heats the matter to extraordinary temperatures, causing it to emit light and radiation. For a short time, perhaps a few days or weeks, the collision site glows like a newborn star, a brief spark in the darkness. And then it fades. The light dies away. The debris cools and disperses, and the darkness returns. These collisions are the only natural light sources in the universe at this stage. They are rare, widely separated in both space and time. If you were somehow floating in this future galaxy, you might wait 1,000,000 years between flashes. You would spend your time in near total darkness, surrounded by invisible remnants, feeling their gravity but seeing nothing. And then, somewhere far away, a brief flare would light up a tiny patch of the sky for a moment before fading back into the black. It is a lonely universe, a quiet universe. The vibrant stellar ecosystems that once filled galaxies, the complex interplay of star birth and death, of supernovae enriching the interstellar medium, of young stars clearing out gas clouds and triggering new waves of formation, all of that is over. What remains is static, unchanging except on the slowest of timescales. The era of light has ended. The era of darkness has begun. But even in this darkness, the universe is not yet done changing. Gravity, the weakest of the fundamental forces, but the one that acts over the longest distances and the longest times, continues its patient work. The stellar remnants orbiting within galaxies are not in stable, eternal orbits. They interact with each other gravitationally, giving little tugs and pulls as they pass, exchanging energy and momentum. Over immense spans of time, these interactions add up. Some remnants gain energy in these exchanges. They move faster, their orbits carrying them farther from the galactic center. Eventually, some gain enough energy to escape the galaxy entirely. They are flung out into intergalactic space to wander alone forever, no longer bound to any larger structure. This process is called evaporation, and it is the gravitational equivalent of molecules evaporating from the surface of a liquid. Other remnants lose energy. They move slower, their orbits decaying, spiraling inward toward the galactic center. And at the center of every galaxy, there is a supermassive black hole. These monsters, millions or billions of times the mass of the sun, are the gravitational anchors of galaxies. As remnants spiral inward, They eventually encounter the event horizon of the central black hole and fall in. They are swallowed, their mass added to the black hole's mass, and they disappear from the universe. This process, the gradual evaporation of galaxies and the feeding of central black holes, takes an almost unimaginable amount of time. Current estimates suggest that a typical galaxy will evaporate most of its stellar remnants over a timescale of roughly 10 to the 19th years. That is 10 billion years, 10 quintillion years, 1,000 trillion times the current age of the universe. Let that number rest in your thoughts without trying to hold it. It is a number that means nothing in human terms. It is simply very, very long. And during all that time, the galaxy slowly dissolves. Most of its remnants are ejected into intergalactic space. A smaller fraction spirals inward and is consumed by the central black hole. What is left, after 10 to the 19th years, is mostly just the black hole itself, now grown fatter by consuming perhaps 10 or 20% of the galaxy's original stellar mass, floating alone in space. And the universe around this remnant is vast beyond description. By this point, the expansion of the universe, driven by dark energy, has carried other galaxies far, far away. The distances between galaxy clusters, already enormous in our era, have grown by factors of billions or more. Light from one galaxy cluster can no longer reach another. Each cluster, each collection of merged galaxies and their central black holes, has become an island universe, causally disconnected from all others. If you were somehow existing at this epoch, floating in space near one of these black holes, the sky around you would be entirely, perfectly black. No stars, because they have all died. No galaxies, because they have all been carried beyond the cosmic horizon by expansion. No cosmic microwave background, because it has been redshifted into undetectability. There is only darkness in every direction. The only thing you could detect would be the black hole itself, and that only through its gravitational field. You would feel its pull, feel your orbit curving around it, but you would see nothing. This is the universe at 10 to the 19th years. A collection of isolated black holes, each one surrounded by a sparse halo of ejected stellar remnants, separated by distances so vast that no signal can cross between them. It is a universe that has fragmented into disconnected pieces, each one alone, each one slowly evolving according to its own internal dynamics. And still, we are not at the end. The black holes remain, and black holes, as we will see, have their own strange fate awaiting them. For now, let the image of this dark universe settle into your mind. Let yourself feel the emptiness, the silence, the vast separations. There is a certain peace in it, if you let yourself accept it. This is the universe stripped down to its simplest components. No complexity, no structure, no light. Just gravity and darkness and the slow, slow dance of cooling remnants and patient black holes. It is a universe that has forgotten almost everything. The stars, the galaxies, the rich structures and patterns that once filled space. All of it is gone or transformed beyond recognition. And yet, in a strange way, it is also a universe that has achieved a kind of stability. There are no more violent supernovae, no more colliding galaxies, no more sudden bursts of star formation or dramatic transformations. There is only the slow gravitational evaporation of remnants, the patient cooling of matter, and the expansion of space carrying everything farther and farther apart. The universe has entered its long middle age, and it will stay in this state for a very, very long time, far longer than the stellar age lasted. The age of red dwarfs stretched across tens of trillions of years. The age of black dwarfs and evaporating galaxies will stretch across quintillions. And even that, as vast as it is only a prelude to something longer still. But we are not there yet. For now, rest in this dark, quiet universe. Let its emptiness become a kind of meditation. Breathe slowly and imagine floating in that darkness, weightless, timeless, alone but not lonely. There is nothing to disturb you, nothing to demand your attention, only the faint pull of distant gravity and the perfect silence of space. Let that silence deepen, let it fill you, and let yourself drift, slowly, gently, deeper into calm. We find ourselves now in a universe almost unimaginably different from the one we began with. Trillions upon trillions of years have passed. The stars have all gone out. Galaxies have evaporated, their remnants scattered or swallowed. And what remains is a cosmos populated almost entirely by objects that no longer shine. Black dwarfs, neutron stars, and black holes, drifting through an ever-expanding void. This is the age of degenerate matter, a long, slow epoch measured not in billions or trillions of years, but in quintillions and beyond. Degenerate matter is one of the strangest states of matter that physics allows. It is what happens when ordinary atomic structure breaks down under extreme pressure. In a white dwarf, which becomes a black dwarf after cooling, the electrons that once orbited atomic nuclei in neat shells have been squeezed so tightly that they can no longer be associated with individual atoms. They form a quantum mechanical fluid, a sea of electrons filling all available space, with the atomic nuclei floating in this sea like ions in a dense plasma. But this is not an ordinary plasma. The electrons obey the Pauli exclusion principle, which states that no two electrons can occupy exactly the same quantum state. As more and more electrons are crammed into a smaller and smaller space, they are forced to occupy higher and higher energy states. This creates a pressure called degeneracy pressure that has nothing to do with temperature. Even if you could cool a white dwarf to absolute zero, removing all thermal energy, the degeneracy pressure would remain, holding the star up against gravitational collapse. A black dwarf, then, is a sphere of this strange matter. Carbon and oxygen nuclei, or in the case of low-mass remnants, helium nuclei, packed together in a crystal lattice, surrounded by a degenerate electron sea. The density is extraordinary. A teaspoon of white dwarf matter would weigh several tons on Earth. The material is so incompressible that it behaves more like a solid than a gas, even though it is far denser than any solid we know. And it is cold. By the time a white dwarf has cooled into a black dwarf, trillions of years after its formation, it has radiated away almost all of its thermal energy. Its temperature may be only a few degrees above absolute zero, barely distinguishable from the background temperature of space itself. It no longer glows. It no longer emits any detectable radiation. It simply exists, a dark, cold, incredibly dense sphere drifting through space. Neutron stars are even more extreme. These are the remnants of more massive stars, stars that were too heavy to become white dwarfs. When such a star's core collapses, the pressure becomes so intense that protons and electrons are forced to merge, forming neutrons. The result is a sphere of almost pure neutron matter, held up by neutron degeneracy pressure rather than electron degeneracy pressure. A neutron star is only about 20 kilometers across, roughly the size of a city, yet it contains more mass than the Sun. A teaspoon of neutron star matter would weigh 1 billion tons. Like white dwarfs, neutron stars are born hot, but have no internal power source. Over trillions of years, they too cool, radiating away their heat, until they reach the ambient temperature of the universe. They become cold, dark neutron stars, invisible and nearly inert. These objects, black dwarfs and cold neutron stars, are extraordinarily stable. Once formed and cooled, they can persist essentially unchanged for unimaginable spans of time. There is nothing left to happen to them, no internal processes to drive change. They are frozen configurations of degenerate matter, suspended in a universe that has grown quiet and still. But stable does not mean eternal. Even degenerate matter is subject to processes that, given enough time, will alter it or destroy it. And the timescales for these processes are so long that they make even the age of red dwarfs seem brief. One possibility, still theoretical but supported by some extensions of the standard model of particle physics, is that protons eventually decay. Protons are the nuclei of hydrogen atoms and the building blocks of all heavier nuclei. They are normally considered stable, with no known process that can cause them to disintegrate. But certain theories suggest that protons may have an extremely long but finite lifetime, perhaps around 10 to the 36th years. 10 to the 36th years. Write it out, and it looks like this. 1 with 36 zeros after it. 1 undecillion years. It is a number so large that it loses all meaning. The current age of the universe, 14 billion years, is utterly negligible in comparison. Even the trillions and quintillions of years we have already discussed are tiny fractions of this timescale. If protons do decay, then all atomic nuclei are ultimately unstable. A black dwarf, composed of carbon, oxygen, or helium nuclei, will slowly dissolve as its protons decay one by one, turning into lighter particles and radiation. The process would be incredibly slow. In any given year, only a tiny fraction of the protons in a black dwarf would decay. But given 10 to the 36th years, eventually all of them would. The black dwarf would slowly evaporate, not by emitting heat, but by literally falling apart at the subatomic level. The same fate would await neutron stars, though the details are more complex. Neutrons are not fundamental particles. They are made of quarks held together by the strong nuclear force. If protons decay, it is likely that neutrons do as well, or can be transformed into particles that do. Over unimaginable timescales, even a neutron star would dissolve into radiation and perhaps a few stable particles like electrons and positrons. Current experiments searching for proton decay have found no evidence for it, and they have set lower limits on the proton lifetime that rule out some of the simpler theories. But other theories predict lifetimes much longer than current experiments can probe. The question remains open. Protons may be truly stable, or they may have lifetimes of 10 to the 36th years or even longer. We do not yet know. If protons do not decay, then black dwarfs and neutron stars will persist essentially forever, or at least until other processes come into play. But even if protons are stable, these objects are not entirely safe. Quantum mechanics allows for processes that, while extraordinarily unlikely, become possible over sufficiently long times. One such process is quantum tunneling. In quantum mechanics, particles do not have definite positions. They exist in a kind of probabilistic cloud, and there is always a tiny chance that they will be found in a location where classical physics says they should not be. For ordinary matter at ordinary temperatures, this effect is negligible. But for cold, dense objects like black dwarfs, and over timescales of 10 to the 36th years or more, quantum tunneling can allow the atoms in the dwarf to rearrange themselves into more stable configurations. The most stable configuration of matter at extremely high densities may not be ordinary atomic nuclei. It may be something more exotic, like a lump of iron-56, the most stable nucleus, or even stranger forms of quark matter. Given enough time, a black dwarf might quantum tunnel its way into a different state, transforming from a sphere of carbon and oxygen into a sphere of iron, or into a single enormous nucleus held together by neutron degeneracy pressure. These transformations would release energy, causing the object to warm briefly before cooling again. But the timescales are so long, and the probability of tunneling so low, that these events would be extraordinarily rare, even by the standards of the deep future we are exploring. Another possibility involves the slow gravitational contraction of remnants through radiation of gravitational waves. Any system with mass that is not perfectly spherical and static will emit gravitational waves, ripples in spacetime that carry away energy. For ordinary stars and stellar remnants, this effect is utterly negligible. But over timescales of 10 to the 40 or 50 years, even the tiny imperfections in a black dwarf shape or the slight wobble from a long-ago collision could radiate away enough energy to cause the object to contract slightly, perhaps triggering quantum mechanical changes in its interior structure. All of these processes are theoretical, operating on timescales so long that no experiment could ever test them directly. We infer their possibility from the laws of physics as we understand them, but there is much we do not know. The behavior of matter over timescales of 10 to the 36th years is simply beyond our direct experience or testing. What we can say with confidence is this: the black dwarfs and neutron stars that fill the universe at this stage represent matter in its most stable known forms. They are the endpoints of stellar evolution. They are what remains when all the energy sources are exhausted, all the fusion has stopped, all the heat has radiated away, and they will persist, essentially unchanged, for time spans that dwarf everything that has come before. Imagine, if you can, the patience of these objects. A black dwarf was once a star. It once shone with light, fusing hydrogen, warming planets, perhaps nurturing life. It went through all the stages of stellar evolution, from main sequence to red giant to white dwarf, processes that took billions of years. And then it cooled, a process that took trillions of years. And now it drifts, dark and silent, for quintillions of years or longer. It has spent more time as a cold remnant than it spent as a living star by factors of millions or billions. Its existence is now defined entirely by waiting. And what is it waiting for? Nothing, in a sense. It has no purpose, no destination. It simply exists, following the laws of physics, persisting because there is no process available to destroy it quickly. It is matter in its most reduced form, stripped of energy, stripped of complexity, stripped of change. It is the universe's way of holding on to mass when there is nothing left to do with it. For a mind contemplating this, there is something both melancholic and strangely restful about it. These objects are beyond time in a certain sense. They change so slowly that for all practical purposes they are eternal. They have reached a state of such profound stability that they can wait out almost any span of years without being meaningfully altered. And the universe around them is equally still. By this point, perhaps 10 to the 20th or 30th years into the future, the expansion of space has carried the descendants of different galaxy clusters so far apart that they are no longer in causal contact. Each isolated region contains a supermassive black hole, surrounded by a sparse halo of ejected black dwarfs and neutron stars. And between these regions, nothing. Empty space, expanding, growing ever more empty. If you could exist in this universe, you would be surrounded by perfect darkness and perfect silence. No light to see, no sound to hear, no radiation to detect except perhaps the faintest whisper of quantum fluctuations in the vacuum itself. You would feel gravity, the slow pull of nearby remnants, the stronger pull of the central black hole if you were close to one. But otherwise, nothing would indicate the passage of time. 1 million years would feel the same as 1 billion. 1 billion the same as 1 trillion. Time loses its texture when nothing changes. This is the age of degenerate matter, an age defined not by events, but by stillness. An age where the universe has achieved a kind of equilibrium, a balance between the expansion of space and the gravitational binding of isolated remnants. It is an age that will last far longer than any age before it. The stellar age, from the first stars to the last red dwarfs, lasted roughly 100 trillion years. The age of degenerate matter, from the cooling of the last white dwarfs to the decay of protons or the final evaporation of black holes, may last 10 to the 36th years or more. The universe has slowed to a crawl. It is not dead, not quite. There are still particles, still fields, still the slow working of quantum mechanics and gravity. But it has entered a state so close to stasis that the difference becomes philosophical rather than practical. And yet, even in this stillness, there are depths we have not yet reached. The black holes remain. And black holes, as strange as they are, do not last forever. They have their own unique fate, their own timeline of decay. And that decay, when it comes, will represent one of the universe's final transformations, a last flicker of activity before an even deeper silence falls. But we are not quite ready for that yet. For now, rest in the age of degenerate matter. Let your mind settle into the image of a dark, cold universe, filled with invisible remnants, changing so slowly that change itself becomes meaningless. There is a strange comfort in this image, if you let yourself feel it. It is a universe without urgency, without pressure, without the need for anything to happen. It simply is, and will continue to be, for timescales that reduce all of human history to less than the blink of an eye. Breathe slowly. Let the vastness of this age fill your awareness. Let the darkness be a kind of blank canvas, restful and calm. And let yourself drift, as the black dwarfs drift, patient and still, through the long, long middle years of a universe that has forgotten how to shine. In the profound darkness and stillness of the universe at 10 to the 36th years and beyond, one type of object remains that we have not yet fully addressed. Black holes. These strange regions of space-time, formed from the gravitational collapse of the most massive stars and grown over eons by consuming nearby matter, are among the most mysterious objects in physics. They are not made of matter in the ordinary sense. They are configurations of space-time itself, regions where gravity has become so strong that it warps the fabric of reality into a shape from which nothing, not even light, can escape. A black hole has a boundary called the event horizon. This is not a physical surface, but a mathematical boundary in space-time. Cross the event horizon moving inward, and you can never return. All paths through space-time lead deeper in, toward the singularity at the center. Even light, traveling at the maximum possible speed, cannot escape. From outside, the event horizon appears as a perfectly black sphere, absorbing everything, emitting nothing. For most of the universe's history, black holes have been relatively rare and unremarkable on cosmic scales. Stellar mass black holes, formed from massive stars, are scattered throughout galaxies. Supermassive black holes, millions or billions of times more massive, sit at the centers of most galaxies, including our own Milky Way. These central black holes grow slowly by accreting gas and occasionally by merging with other black holes when galaxies collide. But for the most part, black holes are passive objects. They sit in space, warping it with their gravity, but not actively doing much unless material happens to fall near them. As the universe ages and the stars go out, black holes become increasingly dominant. In the age of degenerate matter we just explored, the universe is filled with black dwarfs and neutron stars, but the most massive objects are the supermassive black holes at the centers of the former galaxies. These black holes have grown over trillions of years, swallowing stellar remnants that spiraled inward and merging with other black holes from galaxy collisions. A typical supermassive black hole at this epoch might have a mass of billions or even hundreds of billions of times the mass of the Sun, and they will continue to grow slowly. As the remnants in the surrounding halo continue their gravitational dance, occasionally one will lose enough energy to spiral all the way into the central black hole. Each time this happens, the black hole gains a tiny bit more mass. Over timescales of 10 to the 20th years or more, perhaps 10 or 20% of the galaxy's original stellar mass ends up inside the central black hole. The rest is ejected into intergalactic space. Once this process is complete, the black holes sit alone, surrounded by vast empty space. Other black holes exist, the remnants of other galaxies and clusters, but they are now so far apart that they can no longer interact. The expansion of the universe has carried them beyond each other's cosmic horizons. Each black hole is isolated, alone in its own region of space, disconnected from everything else. And now we must confront one of the most profound predictions of theoretical physics. Black holes, despite their name, are not entirely black. They emit radiation. This was discovered theoretically by Stephen Hawking in 1974, and it has profound implications for the far future of the universe. The mechanism is subtle and rooted in quantum mechanics. Near the event horizon of a black hole, the intense curvature of space-time creates conditions where particle-antiparticle pairs can spontaneously appear from the vacuum. Normally, these pairs annihilate almost instantly, returning their energy to the vacuum. But near the event horizon, something different can happen. One member of the pair might fall into the black hole while the other escapes. To an outside observer, it appears as though the black hole has emitted a particle. This is Hawking radiation. It is extraordinarily faint. The temperature of the radiation is inversely proportional to the mass of the black hole. A stellar mass black hole, with a mass of 10 suns, has a Hawking temperature of only about 1/millionth of a degree above absolute zero. A supermassive black hole with a mass of 1 billion suns has a temperature 1 billion times lower still, utterly negligible. But Hawking radiation carries energy away from the black hole. And since energy and mass are equivalent, this means the black hole is slowly losing mass. It is evaporating. The process is incredibly slow for large black holes, but it is inexorable. Given enough time, any black hole will completely evaporate, leaving behind only the faint radiation it emitted. How long does this take? The lifetime of a black hole due to Hawking radiation depends on its mass. A stellar mass black hole, 10 times the mass of the Sun, will evaporate in roughly 10 to the 67th years. A supermassive black hole with 1 billion solar masses will last about 10 to the 100th years. These are timescales so enormous that they make even proton decay seem fast by comparison. 10 to the 67th years. 10 to the 100th years. Let these numbers wash over you without trying to grasp them. They are beyond comprehension, beyond meaning in any ordinary sense. They are simply very, very long. Longer than any timescale we have yet discussed. Longer than the age of stars. Longer than the age of degenerate matter. Longer than the hypothetical proton decay timescale. This is the timescale on which black holes, the last massive objects in the universe, finally disappear. The process of black hole evaporation is not uniform. For most of a black hole's lifetime, the evaporation is so slow that nothing seems to change. The black hole sits in space, barely radiating, imperceptibly shrinking. But as it loses mass, its temperature increases and the evaporation rate speeds up. The smaller the black hole, the faster it evaporates. In the final stages, the process accelerates dramatically. The last few years of a black hole's existence see it shrink rapidly, growing hotter and hotter, until in a final burst of radiation it disappears entirely. But that final burst is still unimaginably far in the future. For now, in the epoch we are exploring, the black holes have not yet begun to evaporate significantly. They sit in space, cold and dark, their Hawking radiation so faint that it contributes virtually nothing to the universe's energy content. They are simply waiting, patient as only a black hole can be, for the slow quantum process of evaporation to run its course. Imagine, if you can, existing near such a black hole. You are in empty space, far from any remnants, alone in the darkness. The black hole itself is invisible, a region of perfect blackness against an already black sky. You cannot see it, but you can feel it. You orbit around it, held by its gravity, tracing a slow ellipse through the void. Time passes. Years, centuries, millennia, eons. Nothing changes. The black hole remains. You orbit. The universe expands around you, carrying other black holes farther and farther away, until yours is the only massive object in your observable universe. And still time passes. Millions of years. Billions. Trillions. The black hole evaporates so slowly that you cannot detect any change. 10 to the 40th years pass. 10 to the 50th. 10 to the 60th. And finally, after 10 to the 67th years, if you have somehow persisted all that time, you would begin to notice something. The black hole is shrinking. Slowly at first, but detectably. It is radiating more than it did before, glowing with a faint, invisible heat. Its mass is decreasing. Its event horizon is contracting. And then the process accelerates. Over the final million years, the black hole that has existed for 10 to the 67th years shrinks rapidly. It grows hotter, its Hawking radiation intensifying, shifting from long radio waves to microwaves to infrared to visible light. In the final seconds, the black hole glows brilliantly, white hot, pouring out more energy in those moments than it emitted over its entire previous lifetime. And then, in a final flash, it is gone. The black hole has completely evaporated. What remains is only radiation, expanding outward in a spherical shell, growing ever more diffuse as it spreads through space. This is the fate of every black hole. Stellar mass black holes evaporate around 10 to the 67th years. Supermassive black holes last longer, but not forever. A black hole with 1 billion solar masses evaporates around 10 to the 100th years. Even the largest black holes imaginable, formed from the merger of many supermassive black holes, cannot last beyond 10 to the 110th years or so. After that point, after 10 to the 110th years, there are no black holes left. They have all evaporated. The universe contains no massive objects at all. The universe contains no massive objects at all, assuming protons have also decayed by this point. What remains is only radiation and perhaps a few stable particles, electrons and positrons and photons, spread across an incomprehensibly vast volume of space. This is the black hole epoch, an age when black holes are the only significant massive objects left, sitting alone in their isolated regions of space, slowly evaporating through Hawking radiation. It is an age defined by waiting. The universe is simply waiting for quantum mechanics to finish its work, for the black holes to radiate away their mass, for the last remnants of structure to dissolve into radiation. There is something almost meditative about this epoch. Nothing dramatic happens. There are no collisions, no explosions, no sudden transformations. There is only the slow, patient process of evaporation, operating over timescales so long that they numb the mind. The universe has entered a state of profound stillness, broken only by the faint quantum hiss of black holes radiating into the void. For most of this epoch, the universe would appear entirely dead. The black holes emit so little radiation that they might as well be emitting none. The temperature of the universe, set by the cosmic microwave background, has by now cooled to almost absolute zero. The wavelength of the background radiation has been stretched by cosmic expansion to scales of light years or more, making it undetectable by any conceivable instrument. Space is cold, empty, and dark, and yet, on the deepest level, the universe is not static. The black holes are changing, however imperceptibly. Mass is being converted to radiation. The total entropy of the universe, a measure of disorder, is increasing as the black holes evaporate. The universe is moving toward a state of maximum entropy, a state called heat death, where all energy is uniformly distributed and no further change is possible. This is the inevitable endpoint predicted by the laws of thermodynamics. The universe began in a highly ordered state, with all its energy concentrated in a hot, dense Big Bang. Ever since, entropy has been increasing. Stars form and die, increasing entropy. Black holes form and evaporate, increasing entropy. The universe expands and cools, spreading its energy over ever larger volumes, increasing entropy. And eventually, the universe reaches a state where entropy can increase no further. All black holes have evaporated. All matter has decayed or been converted to radiation. All the radiation has been redshifted to infinitesimal energies. And the universe becomes a cold, empty, uniform sea of extremely dilute radiation and particles with no gradients, no structure, no way for anything interesting to happen ever again. This is heat death, and the black hole epoch is the final chapter before heat death is achieved. It is the universe spending the last of its concentrated energy, the mass locked in black holes, converting it to radiation and letting that radiation disperse into the void. Once the black holes are gone, there is nothing left but the final state. The universe will have reached its end, not in a dramatic collapse or explosion, but in a gentle fade into uniformity. As you contemplate this, let the image of a solitary black hole fill your mind. See it sitting in darkness, invisible, silent, slowly radiating its essence away into the void. Feel the patience of it. Feel the timescales involved, so long that all of human history is less than an instant. Let the vastness of it wash over you, not as something frightening or sad, but simply as the way things are. This is the universe following its own nature, obeying the laws of physics, unfolding in the only way it can. There is a strange peace in accepting this. The universe is not eternal. Nothing lasts forever. Nothing lasts forever. Not stars, not planets, not galaxies, not even black holes. Everything that has a beginning has an ending. But the endings are so far in the future, so gentle and slow, that there is no urgency, no reason for fear. The universe is simply being itself, and it will continue being itself for timescales that make forever seem almost real. Breathe slowly and let yourself drift in this understanding. The black holes will evaporate. The universe will cool. Entropy will increase. And eventually, everything will reach a state of rest. But that is still so far ahead that it might as well be another universe entirely. For now, in this moment, as you lie here breathing softly, the black holes are still there, still waiting, still patient. And so can you be. Patient, still, at rest in the knowledge that the universe, for all its vastness and strangeness, is following a path that leads eventually to silence and peace. We have reached a point in our journey where even the concept of matter itself begins to dissolve. The black holes have evaporated. The universe at 10 to the 100th years or beyond is now truly empty of any massive objects. What remains, if protons are stable, are the cold remnants we discussed earlier, black dwarfs, neutron stars, and the particles ejected from black hole evaporation. But there is another possibility, one that takes us even deeper into the dissolution of structure. The possibility that protons themselves are not eternal. A proton is one of the fundamental building blocks of ordinary matter. Every atomic nucleus contains protons. A hydrogen nucleus is simply a single proton. Heavier elements contain multiple protons along with neutrons. For most of the 20th century, protons were thought to be absolutely stable, unchanging across all time. But certain theories developed in the 1970s and beyond, theories attempting to unify the fundamental forces of nature, predict that protons may eventually decay. The timescale for proton decay, if it occurs at all, is extraordinarily long. Current experimental limits place the proton lifetime at greater than 10 to the 34th years, and many theories predict lifetimes around 10 to the 36th years or even longer. This is a span of time so vast that it dwarfs even the evaporation time of supermassive black holes. It is a number with 36 zeros, 1 undecillion years, a trillion years. If protons decay on this timescale, then every atomic nucleus in the universe is slowly disintegrating. The process is so slow that in any given year, only an infinitesimal fraction of protons decay. But given enough time, all of them will. And when they do, the matter they compose simply falls apart. Imagine a black dwarf, a cold sphere of carbon and oxygen nuclei, floating in the darkness. Each carbon nucleus contains 6 protons. Each oxygen nucleus contains 8. If protons decay, then over timescales of 10 to the 36th years, these nuclei will gradually dissolve. One by one, protons in the nuclei will decay, typically into lighter particles like positrons, neutrinos, and gamma rays. The nucleus becomes unstable, breaks apart, and the fragments themselves eventually decay. The black dwarf does not explode. It does not heat up significantly. It simply evaporates at the subatomic level, its atoms falling apart one nucleus at a time, releasing faint bursts of radiation that disperse into space. The same fate awaits neutron stars, though the mechanism is slightly different. Neutrons are not fundamental particles. They are made of quarks. If protons decay, then the quarks that make up neutrons likely undergo similar processes. A neutron star, that incredibly dense sphere of neutron matter, would slowly dissolve over 10 to the 36th years, its neutrons decaying or transforming into lighter particles. What was once the collapsed core of a massive star becomes a diffuse cloud of radiation and perhaps a few stable particles like electrons and positrons. This process, if it occurs, represents the complete dissolution of ordinary matter. Everything made of atoms, everything made of protons and neutrons, eventually decays into radiation and lighter particles. The black dwarfs disappear. The neutron stars disappear. The black dwarfs disappear. The neutron stars disappear. Even the particles floating in intergalactic space, the hydrogen atoms and helium atoms that were never incorporated into stars, decay. The universe is stripped of all ordinary matter, leaving only radiation, electrons, positrons, and perhaps neutrinos and photons. Let that image settle into your mind. A universe with no atoms, no nuclei, no protons or neutrons, just electrons, positrons, photons, and neutrinos spread across a volume of space so vast that the density is almost zero. This is the universe at 10 to the 36th years, assuming proton decay occurs. The radiation emitted by proton decay would initially carry some energy, but as the universe continues to expand, that radiation is redshifted to longer and longer wavelengths, lower and lower energies. By the time the last protons have decayed, the radiation has been stretched across such enormous scales that it is effectively indistinguishable from the vacuum itself. The photons have wavelengths measured in light years or longer. Their energy is infinitesimal. What remains is an extraordinarily dilute sea of particles and radiation. The density of matter and energy in the universe has been driven down to almost nothing by the relentless expansion of space. If you were to pick a random cubic light year of space at this epoch, you might find a single electron, or a single photon, or nothing at all. The universe has become as empty as it is possible to be while still containing anything. And yet, even in this emptiness, there is a kind of structure. The particles are not distributed perfectly uniformly. Quantum fluctuations, the random variations that arise from the uncertainty principle, create tiny variations in density from place to place. In some regions, there might be slightly more particles. In others, slightly fewer. In others, slightly fewer. These fluctuations are incredibly small, but they are real. Over unimaginable timescales, perhaps 10 to the 150th years or beyond, these quantum fluctuations might lead to rare and strange events. In an extremely dilute gas of electrons and positrons, there is a tiny probability that two of these particles will randomly come close enough to interact. If an electron and a positron meet, they annihilate, producing photons. If two electrons come close, they might scatter off each other, exchanging momentum. These interactions are so rare that you might wait 10 to the 100th years between events in any given region of space. But the universe is vast, and time is unlimited. Rare events, given enough time, become inevitable. Occasionally, somewhere in the unimaginable expanse, two particles interact. A brief flicker of activity in an otherwise unchanging void. There is even a theoretical possibility, explored by some cosmologists, that quantum fluctuations could occasionally produce more complex structures. In an infinite span of time, quantum mechanics allows for the possibility that particles could spontaneously arrange themselves into ordered configurations. The probability is almost zero, but almost zero is not quite zero. Over timescales of 10 to the 100th years, or even more absurdly long times, quantum fluctuations might briefly assemble atoms, molecules, or even macroscopic objects. This idea, sometimes called Boltzmann brains after the physicist Ludwig Boltzmann, suggests that in a sufficiently old universe, it is more probable for a conscious observer to spontaneously fluctuate into existence than for one to have evolved through natural processes. This is deeply strange and unsettling, and it is one of the puzzles that cosmologists studying the far future must grapple with. If the universe truly lasts forever and quantum mechanics allows for such fluctuations, then almost anything becomes possible given enough time. But these are speculative ideas, and the timescales involved are so extreme that they lose all practical meaning. What we can say more confidently is that after proton decay, the universe enters a state that is as close to nothing as it is possible to get while still being something. It is a state of maximum entropy, maximum disorder, minimum structure. It is the heat death we have been moving toward all along. In this state, there are no energy gradients, no differences in temperature from place to place, no concentrations of matter or radiation. Everything is spread uniformly, or as uniformly as quantum mechanics allows, across all of space. And without gradients, without differences, there can be no change. No flow of energy from hot to cold, no gravitational collapse of matter, no chemical reactions, no life. Nothing happens because there is nothing left to make things happen. This is the ultimate endpoint of the second law of thermodynamics, the law that states entropy always increases in a closed system. The universe began in a state of low entropy, with all its energy concentrated in the Big Bang. Since then, entropy has been increasing steadily. Stars formed and died, increasing entropy. Black holes formed and evaporated, increasing entropy. Matter decayed, increasing entropy. And now, at 10 to the 36th years or beyond, entropy has reached its maximum. The universe has achieved thermodynamic equilibrium. And in equilibrium, time loses its meaning. Nothing changes, nothing evolves, nothing happens. There is a profound melancholy to this vision of the universe's end. Everything that has ever existed, every star that has ever shone, every planet that has ever formed, everything that has ever existed, every star that has ever shone, every planet that has ever formed, every life that has ever lived, all of it leads eventually to this. Perfect emptiness, perfect stillness, perfect silence. The universe does not end in fire or ice, but in a gentle fade into uniformity. It does not collapse back into a singularity, giving the possibility of rebirth. It simply expands forever, cooling forever, becoming emptier and emptier, until there is almost nothing left. And yet, there is also something strangely comforting about this vision. The universe is not destroyed. It does not suffer some violent catastrophe. It simply follows the laws of physics to their natural conclusion. It spins its energy slowly, carefully, stretching its existence across the longest possible span. It does not rush toward its end. It takes all the time there is, and then more. For us, living in the bright age of stars, this far future is so remote that it might as well not exist. It will have no impact on us, no effect on anything we or our descendants might do for billions of years to come. It is simply a fact about the universe, a truth about the way things are, that we can contemplate from our safe position in the present. And in contemplating it, we gain perspective. We see that our moment, this brief flicker of light and warmth and structure, is precious because it is temporary. The universe will not always be like this. It will not always have stars and planets and perhaps life. These things exist now, in this cosmic instant, and then they will be gone. Not soon, but eventually. And that makes them worth appreciating, worth marveling at, worth cherishing. So as you rest here, breathing slowly, let yourself feel gratitude for the present. Gratitude that you exist in a universe that still has stars, that still has structure, that still has light. Gratitude that you exist in a universe that still has stars, that still has structure, that still has light. The protons have not decayed. The black holes have not evaporated. Matter still exists. Energy still flows. And you are here to witness it, to be part of it, to experience this brief moment of cosmic order before the long dissolution begins. Let that gratitude fill you. Let it soften your thoughts and calm your mind. The universe will take care of its own future. It will follow the laws of physics wherever they lead, patiently, inevitably, without regret. And you can do the same. You can follow your own nature, rest in your own present, and let the future unfold as it will. There is nothing to fear. There is only time, vast and patient, carrying everything gently towards stillness. Breathe deeply. Feel the weight of your body, the warmth of your breath, the quiet rhythm of your heart. These are the gifts of the present, the fruits of a universe that still has energy to give. Accept them, rest in them, and let yourself drift, slowly, peacefully, into the deep calm that waits beyond all thinking, beyond all time. Throughout our journey into deep time, there has been one constant force quietly shaping the universe's fate: dark energy. This mysterious component of the cosmos, making up roughly 68% of the universe's total energy content, has been driving the expansion of space at an accelerating rate for billions of years. And as we move into the universe's most distant future, dark energy becomes not just important but dominant, the only significant force still acting on cosmic scales. Dark energy is one of the most profound mysteries in modern physics. We know it exists because we can measure its effects. In the late 1990s, astronomers studying distant supernovae discovered something unexpected. In the late 1990s, astronomers studying distant supernovae discovered something unexpected. The universe's expansion, which had been slowing down due to the gravitational attraction of matter, was actually speeding up. Distant galaxies were receding from us faster than they should be if gravity were the only force at play. This acceleration requires some form of energy that fills all of space, exerting a kind of negative pressure that pushes space apart. This is dark energy. We do not know what it is made of. We do not know why it has the density it does. We do not know if it is truly constant or if it might change over time. What we know is that it is there, and it is causing space itself to expand faster and faster as time goes on. In the early universe, dark energy was negligible. Matter and radiation were dense enough that their gravitational pull dominated. The universe expanded, but gravity slowed the expansion. Over billions of years, as the universe grew larger and matter became more dilute, dark energy became increasingly important. Around 4 or 5 billion years ago, dark energy began to dominate. Since then, the expansion has been accelerating, and it will continue to accelerate. As the universe expands, matter becomes even more dilute, and dark energy becomes even more dominant. The expansion rate increases. Space stretches faster and faster, and this has profound consequences for the far future we have been exploring. One of the most important consequences is the existence of a cosmic event horizon. This is a boundary in space beyond which events can never affect us, no matter how long we wait. It arises because space is expanding so fast at great distances that light emitted from beyond a certain distance can never reach us. The light travels toward us at light speed, but space itself is stretching faster than the light can cross it. The light makes no net progress. It is trapped beyond the horizon. Currently, this cosmic event horizon is roughly 16 billion light-years away. Galaxies beyond that distance, if they emit light today, will never have that light reach us. And as time goes on, this horizon does not move outward, it actually moves inward. Galaxies that are currently within the horizon will eventually cross beyond it. Their light will take longer and longer to reach us, redshifting to longer wavelengths, fading to invisibility, and finally ceasing to arrive at all. Over hundreds of billions of years, most of the galaxies we can see today will disappear beyond the cosmic horizon. Only the galaxies that are gravitationally bound to us, the galaxies in our local group and perhaps our local cluster, will remain visible. These galaxies are close enough that their mutual gravitational attraction overcomes the expansion of space. They will eventually merge into a single large galaxy, as we discussed earlier. But all the other galaxies, the thousands of galaxies visible in deep telescope images, will fade away. By 1 trillion years into the future, an observer in our merged galaxy would see almost nothing beyond their own galaxy. A few nearby galaxies might still be visible if they are part of the same gravitationally bound group. But the rest of the universe, the vast cosmic web of galaxies and clusters, would be gone, carried beyond the horizon by expansion. The observable universe would shrink to just the local group. And the shrinking does not stop. As acceleration continues, the cosmic horizon moves ever closer. Eventually, even nearby galaxies might cross beyond it if they are not tightly bound. The observable universe becomes smaller and smaller, containing fewer and fewer objects. In the scenarios we explored earlier, where black holes evaporate and matter decays, this process continues. In the scenarios we explored earlier, where black holes evaporate and matter decays, this process continues until each isolated region of the universe contains only a single supermassive black hole remnant and a sparse halo of particles. These regions are causally disconnected from each other. No signal can travel from one to another. Each region is, effectively, its own universe. And within each region, the effects of dark energy become increasingly dominant. In the absence of significant matter, space expands exponentially. This is sometimes called a de Sitter space, named after the physicist Willem de Sitter who studied such solutions to Einstein's equations. In a de Sitter space, distances grow exponentially over time, doubling every so many billions of years, and this doubling continues forever. An object floating in such a space would see the cosmic horizon moving closer and closer. Eventually, The horizon might be only a few light years away, or even less. Beyond that distance, space expands so fast that nothing can reach you. You are trapped in a tiny bubble of observable space, causally disconnected from everything outside. Some physicists have speculated about even more extreme scenarios. If dark energy is not constant but instead grows stronger over time, a possibility called phantom energy, then the acceleration could become so intense that it eventually tears apart all bound structures. First, galaxy clusters would be pulled apart, then galaxies, then star systems, then planets. Eventually, even atoms and subatomic particles would be ripped apart by the expansion of space. This scenario is called the Big Rip, and it would represent a violent end to the universe, in contrast to the gentle fade we have been describing. Current observations, however, suggest that dark energy is consistent with being a cosmological constant, a truly constant energy density. Current observations, however, suggest that dark energy is consistent with being a cosmological constant, a truly constant energy density that does not change over time. If this is correct, then the Big Rip will not occur. Instead, the universe will continue expanding exponentially, but without tearing apart bound structures. Galaxies, or what remains of them, will persist. Black holes will evaporate, as we described. Matter will decay. But the expansion itself will not directly destroy anything. It will simply carry things farther and farther apart. In such a universe, the far future looks like this: isolated bubbles of space, each containing at most a single large black hole and a sparse population of particles. These bubbles are expanding, but nothing within them changes much. The black holes slowly evaporate. The particles drift apart, and space itself grows ever larger, ever emptier, approaching a state of perfect vacuum. The temperature of such a space approaches a minimum value called the de Sitter temperature. This is an extraordinarily low temperature, far colder than the cosmic microwave background is today, colder than anything we can produce in a laboratory. It arises from the quantum properties of the event horizon. Just as black holes emit Hawking radiation, a de Sitter space has a faint thermal radiation associated with its horizon. But the temperature is so low that it is almost meaningless. It is merely the faintest possible whisper of energy in an otherwise empty space. There is something almost abstract about this vision of the far future. It is a universe that has become as simple as possible. No structure, no complexity, no change. Just space, expanding exponentially, filled with an almost perfectly uniform distribution of extremely dilute energy. It is as close to nothing as the universe can get while still existing. And yet, in a strange way, this state is stable. It can persist forever. Unlike a universe filled with matter and stars, which must evolve and change, a de Sitter space can simply continue expanding, unchanging, for eternity. It is the universe in its final equilibrium, its ultimate resting state. For a mind contemplating this, there is a curious sense of peace. The universe is not headed for destruction. It is not collapsing, not ending in fire or catastrophe. It is simply expanding into a state of ever greater simplicity, ever greater emptiness. It is following the most natural path available to it, the path of maximum entropy, maximum uniformity, minimum structure. And in that path, there is a kind of logic, even a kind of beauty. The universe began in a state of incredible order and density. The Big Bang was a configuration of extremely low entropy, with all the energy of the universe concentrated in a tiny volume. From that beginning, entropy has been increasing. Order has been giving way to disorder. Structure has been dissolving into uniformity. And the endpoint of this process is the simple, empty, expanding space we have been describing. It is the universe completing its arc, from complexity back to simplicity, from concentration to diffusion, from activity to stillness. It is not an ending in the sense of ceasing to exist. It is an ending in the sense of reaching a final state from which no further change is possible or necessary. As you breathe slowly, let this image fill your awareness. See the universe expanding, cooling, emptying. See the last black holes evaporating. See the last particles drifting apart. See space itself growing ever larger, ever darker, ever more peaceful. There is no struggle here, no resistance. There is only the gentle unfolding of physical law, carrying everything toward stillness. There is no struggle here, no resistance. There is only the gentle unfolding of physical law, carrying everything toward stillness. And in that stillness, there is rest. The universe is resting, and you can rest with it. Your body can relax into the surface beneath you. Your breath can slow to a gentle rhythm. Your thoughts can quiet, becoming as sparse and simple as the particles in that far future space. There is nothing you need to do, nowhere you need to go. You can simply be suspended in this moment, at peace with the way things are and the way they will be. The dark energy that drives this expansion is not cruel or destructive. It is simply a property of space, doing what space does, expanding and carrying everything along with it. It is the universe making room for itself, creating ever more space in which to exist. And as it does so, it creates the conditions for ultimate peace, ultimate simplicity, ultimate rest. Let yourself sink into that peace. Feel it in your body, in your breath, in your mind. The universe is showing you what it means to let go, to release complexity, to settle into simplicity. And you can follow that example. You can let go of the day's concerns, the mind's chatter, the body's tensions. You can settle simply and completely into rest. The dark energy future is not something to fear. It is simply the universe being itself, following its nature, reaching for equilibrium. And equilibrium is peace. Equilibrium is rest. Equilibrium is the state where all forces balance, where all change ceases, where everything simply is. Breathe that equilibrium into your body. Feel it spreading through your limbs, your chest, your head. Feel yourself becoming as still and peaceful as that far future space. Empty, simple, at rest. This is the gift of deep time. This is the gift of deep time. It shows us that everything eventually comes to rest. And in that knowledge, we can find rest now, in this moment, without waiting billions of years. We can choose to be still, to be simple, to be at peace. And as you make that choice, as you let yourself drift deeper into calm, know that you are aligned with the deepest currents of the universe. You are following the same path it follows, from complexity to simplicity, from activity to stillness, from thinking to simply being. This is the way of all things, and it is available to you now, in this breath, in this moment, in this gentle falling away of everything that is not rest. We have come to the end of our journey through deep time. We have watched the last stars form and fade. We have seen the universe cool and darken. We have followed black holes through their impossibly long evaporation. We have witnessed the possible decay of matter itself. And we have explored the far future shaped by dark energy, a future of expanding emptiness and profound stillness. Now, in these final moments, let us rest in the silence that remains when everything else has fallen away. The universe at 10 to the 100th years, or beyond, is almost indescribable in its simplicity. There are no stars, no planets, no galaxies, no black holes. If protons have decayed, there are no atoms, no ordinary matter at all. What remains is only radiation and perhaps a few types of stable particles, spread so thinly across space that the density approaches zero. Space itself has expanded to unimaginable size. The distances between particles are measured not in meters or kilometers or light years, but in scales that dwarf even the current observable universe. A single photon might travel for billions of years without encountering anything at all. A single photon might travel for billions of years without encountering anything at all. The universe has become, for all practical purposes, empty. And in that emptiness, time loses much of its meaning. When nothing changes, when there are no events to mark the passage of time, what does it mean to say that time is passing? The universe exists, yes. Space continues to expand. Particles continue to move. But these are processes without variation, without novelty, without progression. They simply continue, unchanging, forever. This is what physicists mean by heat death. Not a sudden ending, not a catastrophe, but a state of maximum entropy from which no further change is possible. All the energy that was once concentrated in the Big Bang has been spread uniformly across space. All gradients have been erased. All differences have been smoothed away. And without differences, without gradients, nothing can happen. Life, in any form we can imagine, requires energy gradients. A warm region and a cold region, with energy flowing from hot to cold, a source of fuel and a place to exhaust waste products. Some kind of disequilibrium that can be harnessed to do work, to maintain structure, to preserve complexity against the inexorable slide toward disorder. In a universe at maximum entropy, no such gradients exist. There is nowhere for energy to flow. There is no way to maintain structure. Life, if it has somehow persisted to this point, can persist no longer. Consciousness, too, requires change. Thoughts are processes, patterns of activity unfolding over time. To think requires structures that can store and manipulate information, and those structures require energy to maintain themselves. In a universe without available energy, without gradients, consciousness cannot exist. There is nothing to think with, nothing to think about, no time in which thinking could occur. There is nothing to think with, nothing to think about, no time in which thinking could occur in any meaningful sense. So this far future is not only empty of structure, but empty of observers. There is no one to witness it, no one to experience it, no one to feel its vast silence. It simply is, existing without being experienced, a universe that has outlived everything that could give it meaning. And yet, even in this absolute ending, there is something worth contemplating. This is where everything leads. This is the final state that the laws of physics have been pointing toward since the beginning. The universe was never going to last forever in a dynamic, changing state. It could not sustain stars and galaxies and life indefinitely. It had a finite store of available energy, and once that energy was spent, dissipated, spread too thin to be useful, the story would end. But the story has been long, so incredibly long. From the Big Bang to the heat death spans at least 10 to the 100th years, probably more. That is a length of time so vast that human language has no words for it. The current age of the universe, 14 billion years, is less than a trillionth of a trillionth of a trillionth of that span. The age of stars, 100 trillion years, is only one part in a trillion of the full story. Most of the universe's existence has been spent in darkness, in emptiness, in stillness. The bright age of stars, the era we are fortunate enough to inhabit, is a brief flash at the very beginning. It is the childhood of the cosmos, full of energy and activity and change. But childhood does not last. Adulthood is quieter, longer, more stable. And old age, when it comes, is longest of all. The universe's old age is the heat death we have been describing. It is not a time of suffering or decay. The universe's old age is the heat death we have been describing. It is not a time of suffering or decay in the biological sense. It is simply a time when all the processes have run their course, all the fuel has been spent, all the change that was possible has occurred. It is a time of rest, if rest is the right word for a state without observers to experience it. For us, living in the universe's bright youth, this far future has no direct relevance. It will not affect us or our descendants for billions of years, if we have descendants that long. It is simply a fact about the universe, a truth about the way physical law operates over the longest timescales. And yet, in contemplating it, we gain something valuable. We gain perspective. We see that our moment is special. We live when the universe is still interesting, still dynamic, still full of structure and light. The stars are shining. Planets are orbiting. Life exists, at least here on Earth, and perhaps elsewhere. This is not the way the universe has always been, and it is not the way it will always be. It is a temporary state, a brief window of complexity in a much longer story of simplicity. And that makes it precious. The stars will not shine forever. The galaxies will not turn forever. The opportunity for life, for consciousness, for beings like us to look up at the night sky and wonder about our place in the cosmos, this opportunity is limited. Not by human standards. The window will remain open for billions of years at least. But by cosmic standards, it is brief. And we are fortunate to be living within it. So as you rest here, breathing slowly, let yourself feel that fortune. You exist in a universe that still has light. You are made of atoms forged in stars, atoms that will one day decay or be locked in cold remnants, but for now are organized into the complex structure of your body. You are made of atoms forged in stars, atoms that will one day decay or be locked in cold remnants, but for now are organized into the complex structure of your body. You are conscious, able to think and feel and experience, in a universe that will eventually be empty of all consciousness. You are here, now, in this moment, and that is a gift. Let that sense of gift fill you, not as something you need to grasp or hold on to, but simply as something to acknowledge and appreciate. The universe has given you this moment, this breath, this awareness, and in giving it, the universe has shown you something of its own nature. It has shown you that even in a cosmos governed by entropy, by the inexorable slide toward disorder and simplicity, there can be islands of order. There can be structure, complexity, beauty. There can be stars and planets and life. There can be you. These islands do not last. They cannot last. The second law of thermodynamics ensures that entropy will always increase, that order will always give way to disorder, that the islands of structure will eventually erode and disappear into the sea of maximum entropy. But while they last, they are real. They exist. They matter, at least to themselves, at least in the moment. And this moment is all we ever have. The deep future we have explored, the heat-death trillions upon trillions of years away, is not here now. It is not affecting you now. What is here is this breath, this heartbeat, this quiet awareness of being alive in a universe that is still full of stars. That is enough. That is more than enough. That is everything. As you let yourself drift deeper into sleep, carry this understanding with you. The universe is vast and ancient and will endure for time spans beyond imagining. But you are here now, in the bright age, in the time of light and warmth and structure. The universe is vast and ancient and will endure for time spans beyond imagining. But you are here now, in the bright age, in the time of light and warmth and structure. You are part of the universe's brief complexity, its temporary flowering into order and consciousness. And when you wake, you will still be here, still part of it, still witnessing the cosmos in its prime. The last star will form one day. The final light will fade. The universe will cool into darkness and silence. But not tonight. Tonight, the stars still shine. Tonight, you are here. And that is all that matters. Let your breath slow to almost nothing. Let your thoughts fade like distant stars. Let your body relax completely, surrendering to the surface beneath you, to the gravity that holds you, to the quiet rhythm of your own existence. There is nothing more to do, nowhere to go, nothing to solve or understand or accomplish. There is only this gentle fading, this soft descent into rest. The universe is showing you the way. It is moving slowly and patiently towards stillness, and you can move with it, not in fear of the ending, but in acceptance of the natural rhythm of all things. Everything that begins must end. Everything that is complex must simplify. Everything that is active must eventually rest. This is not tragedy. This is simply the way of the cosmos, the path that all things follow. And in following that path, there is peace. The peace of letting go. The peace of accepting what is and what will be. The peace of resting in the knowledge that you are exactly where you are meant to be, in this moment, in this breath, in this quiet space between waking and sleep. The last star is still in the future, but sleep is here now. And as you slip into it, as your awareness dims and softens and finally releases its hold on waking consciousness, you join the universe in its eternal rhythm. And as you slip into it, as your awareness dims and softens and finally releases its hold on waking consciousness, you join the universe in its eternal rhythm. The rhythm of day and night, waking and sleep, light and darkness, complexity and simplicity, being and not being. Rest now. Let everything go. The universe will continue without your attention. The stars will keep shining. Time will keep passing. And you, released from the need to witness or understand or do anything at all, can simply drift into the deep, peaceful darkness of sleep. A darkness that is not the heat death of the cosmos, but the warm, restful darkness of a mind at peace, a body at rest, a being surrendered to the natural flow of existence. This is the final gift of our journey through deep time. Not fear of the ending, but appreciation of the now. Not anxiety about the far future, but peace in the present. Not struggle against the inevitable, but acceptance and rest. The last star will fade, but you are here now. And now is enough. Now is everything. Now is the only moment that ever truly exists. Rest in it. Sink into it. Let it hold you as you fall gently, softly, completely into sleep. The universe began in light and will end in darkness. But between the beginning and the ending, there is this, a long, patient, beautiful unfolding. Stars shining, galaxies turning, life emerging, consciousness awakening to contemplate its own existence. And then, eventually, the gentle return to simplicity, to stillness, to silence. You have traced that arc tonight. From light to darkness, from complexity to simplicity, from waking to sleep. And in tracing it, you have touched something essential about the nature of existence itself. Everything changes. Nothing lasts. And yet, in the changing and the not lasting, there is profound beauty. Sleep now. Rest in that beauty. Let the last star fade from your mind as you fade into dreams. The universe has told you its story. Now it invites you to rest in the telling, to let go of wondering and simply be, to join the cosmic silence that waits at the end of all things. And in that silence, paradoxically, there is everything. All the light that ever was, all the stars that ever shone, all the life that ever lived, compressed into this single, eternal now, this moment of perfect rest, this breath of peaceful letting go. You are the universe, experiencing itself. And now, the universe is ready to sleep. So sleep, deeply, peacefully, completely. The journey is over. The story is told. All that remains is rest. And rest is enough. Rest is everything. Rest is home. Good night.